Hello. In this video, we'll investigate the behavior of a random variable that is a proportion. And to do this, we'll use the familiar example of flipping a coin and seeing the proportion of times that it comes up heads. We might expect to get heads about 50% of the time, but if we got, say, 45% heads or 60% heads, we wouldn't find that too surprising. But if we got, say, 10% heads, we'd probably find that surprising, because getting 10% or fewer heads is unlikely. It has low probability. In this video, we'll investigate the properties of the probability distribution of the proportion of heads so that we'll be able to quantify this probability. For a while, let's stick with our familiar example of flipping a coin and measuring the proportion of times that it comes up heads. Suppose we flip the coin twice. We could get 0 or 1 or 2 heads. That corresponds to proportions of 0 or 0.5 or 1. Anytime we flip a coin twice, we don't know what proportion of heads we'll get from these choices. That's a random quantity. But we do know the probability distribution that describes how likely we are to get one of these possible proportions. Here it is. We've seen it before. The proportion of half heads is the most likely proportion, since we're flipping a coin that's equally likely to come up heads or tails. Previously, we also saw the probability distribution for the proportions of heads we might possibly get if we flip our coin 3 times, or if we flip it 10 times, or here's the probabilities for the various proportions we could get if we flip it 30 times, and here for 100 times. For each of these, regardless of the number of times we flip the coin, the most likely value for our proportion of heads is, not surprisingly, 1/2. And as the number of flips of the coins increases, the most likely proportions are increasingly concentrated around that value of 1/2. So 1/2 is not just the most likely value for a large number of flips, we're also unlikely to get a proportion that is far from 1/2. We also saw that as the number of flips of the coin increases, the probability distribution for the proportion of heads approaches a normal distribution. This was due to the central limit theorem. As a reminder, the central limit theorem says, if an experiment is repeated over and over, then the probabilities for the average results, or the proportion of successes, will converge to a normal distribution. And we've seen that at play here. The question we'll consider now is, what are the mean and the standard deviation of this normal distribution? Let's introduce some more general notation that we can apply to measuring the proportion of heads when flipping a coin, but we can also use it for studying other proportions, even proportions that might not be 1/2 or 50-50. Here's our general notation. We're going to suppose that we'll carry out n trials, each of which randomly comes up either a success or a failure, and it comes up a success with probability p. So a success could be flipping a coin and getting a head, and then p is 1/2. Or a success could be randomly selecting a voter, and that selected voter is a Green Party supporter. Then p is probably something much smaller than 1/2. We'll use the notation p with a hat on it for the proportion of successes we observe in our n trials. In statistics, the hat notation is often used for an estimate. Here we could talk about the proportion of successes that we observe as an estimate for the probability of getting a success on a trial, and that probability we're calling p, so its estimate is p hat. This quantity p, the probability of getting a success, is a property of our experiment. It's a property of our coin or our population of voters. So it's a fixed quantity. That is, it's not a random quantity. On the other hand, p hat the proportion of successes we get in our n trials, is a random variable. It varies randomly depending on our coin flips or what sample of voters we select. What we'd like to know is the probability distribution for this random variable p hat. We already know it's a normal distribution from the central limit theorem as long as n is large enough for the central limit theorem to apply. And again, what we're looking for now is the mean and standard deviation of this normal distribution. For each of our n trials, we'll record a random variable, we'll call it x, and x will be 1 if the trial comes up a success, and 0 if it doesn't come up a success. X is a Bernoulli random variable with probability p, where p is the probability of a success. The expected value of x can be calculated with the formula for the expectation of a discrete random variable. Remind you, the formula is the expected value of x is the sum over the values it could be times the probabilities of those values. And for a Bernoulli random variable, there's only two values it can be, 0 and 1. So this works out to be 0 times the probability of not getting a success, which is 1 minus p, plus 1 times the probability it comes up 1, a success, which is probability p, and doing the math, this works out to be just p. Similarly, the variance of x can be calculated with the formula for the variance of a discrete random variable. Our formula for the variance of a discrete random variable is the sum over the possible values the random variable can be of that value minus the mean or the expected value squared times the probability of each of the values. And again, since we can only have values 0 or 1, that's 0 minus our expectation, p squared, times the probability of 0, which is 1 minus p, and the value 1 minus p squared times the probability of getting 1, a success, times p, and that works out to be p times 1 minus p. That's the end of the math we're going to do, but we need these two values. Why this is useful is that we can think of our n trials as n independent Bernoulli random variables. We'll call them x1 up to xn. We're estimating the proportion of successes. That's the number of successes divided by the number of trials. To get the number of successes, we just add up the n Bernoulli random variables, since each of them is 1 if it's a success and 0 otherwise, so then it doesn't contribute to the sum. And then to get p hat, the proportion of successes in our n trials, we take this number of successes and just divide it by n. The key thing to note here is that p hat is an average of a bunch of Bernoulli random variables. So that's why the central limit theorem applies to it. It's an average. Knowing this is also useful for finding the mean and standard deviation. We already know in general how the expected value of an average relates to the expected value of an individual random variable, and how the variance of an average relates to the variance of an individual random variable. The expected value of x bar is the same as the expected value of 1x, and the variance of x bar is the variance of 1x divided by n. So how that applies here is then the expected value of p hat is just the expected value of one of our Bernoulli x's, which is p, and the variance of p hat is the variance of one of our Bernoulli random variables, p times 1 minus p, divided by n, since it's an average. And then we can just take the square root. The standard deviation of p hat is the square root of p times 1 minus p over n. So we have that for p hat, the proportion of times we get a success, its expectation is the probability that it happens. Hopefully that sounds right. That sounds like a good property. And indeed it is, if we're using the proportion to estimate the probability of a success. An estimator that has this property, that its expectation is what it's supposed to be, is called an unbiased estimator, and it's a good property for an estimator to have. Something else to note. We observed in the plots of the probability distributions for the proportions of heads when flipping a coin that the standard deviation, the variability, the spread, decreases with n, the number of trials. So the larger our sample size n, the more times we flip the coin or the more times we run our experiment, the more trials we have. The variability in the proportion of times the coin comes up heads or the proportion of successes, whatever a success is, that variability decreases. And now we know exactly how it decreases. To summarize, for large n, p hat, which is the proportion of successes in n trials, where each trial has probability p of success, has approximately this distribution. A normal distribution with mean p and standard deviation, the square root of p times 1 minus p divided by n. For this to be true, we just need n large enough for the central limit theorem to kick in. This probability distribution is going to be very important to us as we go forward and try to do statistical inference on proportions.